Let's look at this extension 2 question from North Sydney Boys. It's a very challenging question if you have never seen similar questions, and let's go. So which of the following is a possible solution of sine x equals 2? If you draw a diagram, sine x is like this, and you draw a line to y equals 2, there is no real solution. But no real solution. If we are extension 2 students, we can have complex solutions. Now we just need to use the complex definition for sine x, and it is this form. I mean, if you don't know this, then there's no way you can do it. If you know this, things become a little easier. You can easily manipulate it into a quadratic equation, and then you solve the quadratic equation to get to this step. And I think by this step it's reasonable difficulty. It's not that hard, but taking ln of both sides, it is a bit challenging. So here I use the ln law, which you should have learned in year 10, that is this. And this step is quite interesting. So e to the power of 2 pi plus 2k pi I equal to I. It's like this. So if it's this, if it's this, it's all I. But we can take ln of both sides to get this result, which is quite novel, and I don't think many people have seen it or can directly think about it. And then we just take one case. It's because we just need to know one solution, not the general solution. We take x equals to 0, and then we go to last step to reach this. So if you're a good extension 2 student, you won't confine to just do this question. You will try to generalize the question and to make sure you understand everything about this type of question, so you can know how to do it. Of, for example, if you meet a similar question, so let's generalize it. Now I want to solve sine theta equals to n, where n equals to all real numbers. So how do we solve this? Of course we know if it's real, because we just go sine theta equals to n. If n is equal from -1 to 1, we just have sine inverse of n plus 2k pi minus sine n plus 2k pi. We have these two. So what I want to verify is if I use the complex number definition of sine, it will still have the same result when n is this, and it will have a complex solution when it's not in this interval. So again, we start from this. Note there is an I here, and many people forget this, and they just the rest is all going to be wrong. So you must make sure you don't forget the I on the numerator. And we have the quadratic, we solve it. So we have the discriminant like this, so it verifies that when n is in this interval, we have a real solution. If it's not, then we don't. So we solve it, we have this result, and you can find out if you plot it out, it's actually the angle is just sine inverse of n, pi minus sine inverse of n, which is consistent as what we will usually do. And if we go out of that definition, it's more than 1. So here we need to have a I here, and then we just again use the quadratic formula to manipulate it. So we reach this, and then we equate everything, and lastly we get this. So the imaginary part is fixed. As you can see, the real part differs by 2 pi every time, and it's just a pretty result, and it's consistent as what we did before. We just use n instead of 2. So let's go to cos. Cos, again the same, use the complex definition, and then we have the discriminant, and then we basically just solve it to be like this. And if you plot it on Algorand diagram, it's again the same. These two angles here, and square root 1 minus sine squared, square root 1 minus squared. So this is alpha, this is minus alpha, and alpha is this, which is consistent. And now I want to solve the complex form, we do exactly the same. Wait, is this right or not? Is this right or not? Yes, it is. It is right. It is right. So it is right, and because in this case it is negative, so in this case this is positive, which is different from sine, and then we get this result. So as always, the real part differs by 2 pi and the imaginary part stay the same. And let's look at the last one, which is we want to solve tan theta. So tan theta, you should know that it looks like this, and it will always have a solution regardless of the n. So you just need to verify that even though you use complex numbers, you will have the same result as you do the normal way. So you start from the complex definition and you go to the quadratic and you get to this step and you get to this step. Sorry, I'm skipping, but you can just pause and see the steps. So last step is this, and you can see it's not really what we want, but this should be kind of a well-known result, and you need to be familiar with the equations like the half angle equation, double angle equation, and if you see this, you can basically find out using this identity, and you use a substitution, you get this. So tan inverse of n is equal to this, and then we get the consistent result, which is exactly what we want. So what we verified here is you can have a complex solution for sine x and cos x, and probably not for tan x. So this question, I mean, you cannot use a calculator because you just, even though they have the complex function, you can't do it. So you just need to know the definition, and you use the complex definition, and then you use quadratic, then you use inverse Euler's formula. Then you should know how to solve it, and it's just 1 mark, so it doesn't hurt if you skip. And there's no way it's gonna be in the HSC because it's so out of the syllabus and it's so without any hint. They will give you a hint if it's in the HSC. And that's this question, and subscribe for more.